So far we've been talking about pure samples of gases, but many gas samples are actually mixtures of several gases rather than just one. So what we call dry air is a mixture containing nitrogen, oxygen, argon, carbon dioxide, and a few other gases in very small amounts. So if we look at the composition of dry air, by volume, it's 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide, and then any other gases are much smaller percentages. What makes it dry air is that it has no humidity in it. Now, that's not the case, just the air in the room, the air outside. There is some humidity in it, so that would affect the composition a little bit. Sometimes we can think of a gas mixture as if it were a single substance. Air is a mixture, but we can measure its pressure, volume, and temperature just like it was pure nitrogen or pure oxygen. Because its pressure, volume, and temperature don't depend on the size of the particles, they only depend on the number. So we can calculate the total moles of molecules even though some of them are different. Gases behave independently. So in the air, the nitrogen is just behaving like it's the only gas in the room. And the oxygen is acting like it's the only gas in the room. They don't interact with each other. So Dalton, same guy who gave us atomic theory, also studied gases and came up with Dalton's law of partial pressures. So when we look at the pressure exerted by a single gas in a mixture of gases, we call that its partial pressure, because that gas is exerting part of the pressure that the whole mixture exerts. And we can calculate the pressure due to a single gas from the ideal gas law. We take the ideal gas law and then solve for P, and we get P equals nRT divided by V. So the pressure of that gas depends on the number of moles, the temperature, and the volume. And so if this is gas N, we put a subscript N there to indicate this is a partial pressure. So what Dalton's law of partial pressure says is that the sum of all the pressures of the individual gases equals the total pressure. This is a little bit like masses of everyday objects. If you have a box of fruit, you have 5 apples and 3 bananas. The mass of the fruit is the sum of the mass of the 3 apples and the 2 bananas. So Dalton's law says the total pressure is equal to the pressure of each component added together. So here's Dalton's law. The total pressure is the pressure of each gas that's in the mixture. Well, we just looked at what would the partial pressure of a gas look like. The partial pressure is equal to the moles of that gas times RT over V. And so for gas B, similar thing, gas C, similar. Because these gases are all in the same container, the temperature and the volume is the same. So we can factor out RT over V and end up with the sum of the moles of the gas. And so we end up with the total pressure is equal to the total moles of gas times RT over V, which is just P equals nRT over V. I'm not going to make you derive that on an exam. If that didn't make much sense to you, that's okay. If we take the ratio of the partial pressure of one gas in the mixture to the total pressure So the pressure of gas A divided by the total pressure. It's sort of like a percentage, right? But we're not multiplying by 100. The partial pressure of A is equal to the moles of A times RT over V. The total pressure is equal to the total number of moles times RT over V. Those cancel out. The ratio of partial pressure to total pressure is equal to the ratio of moles of the one gas to the total number of moles. And this term here has been given a name that's called the mole fraction. It's given the symbol chi. It's a capital chi. Chi sub A is equal to the moles of A over the total number of moles. So we've worked with percentages. A percentage is the part over the whole times 100, right? The part over the whole, this is the fraction. And you multiply by 100 to make it a percentage. The part over the whole. So this is also the part over the whole, but it's moles over total moles. This is pressure of part divided by pressure of the whole. So here what we're doing is we're taking this guy, just looking at this guy is equal to this guy, right down here, and rearranging this a little bit. We're putting P total on the other side. Let me just write this out. So what we're doing there is we're multiplying by P total on both sides. If we do the same thing to both sides of the equation, it's still equal. So these cancel out. So to clean things up, I'm going to erase those. That's where this part came from. This part here is chi A, the mole fraction of A. So we're just subbing in chi A for that term. So the partial pressure of gas A is equal to the mole fraction of gas A times the total pressure. Any questions? When you're using percentages, bless you, and you want to know, well, what's, 25% of something? You can take 25%, divide by 100 to get just the fraction part, 0.25, and you multiply that by the thing, right? This is the fractional amount times the whole thing, and that gives us the part. The partial pressure of a component in a gas mixture is its mole fraction multiplied by the total pressure. That's what that equation was. For gases, the mole fraction is equivalent to percent by volume divided by 100. So nitrogen is 78%, makes up 78% of air. So 78% by volume. We take that percentage, we just divide by 100, and that gives us a mole fraction of 0.78. So that's equal to chi for nitrogen. So if the total pressure is 1 atmosphere, the pressure of nitrogen equals the mole fraction of nitrogen times the total pressure. That's using the equation. We can also think through this using percentages. 78% by volume. 78% of this 1 atmosphere is from the nitrogen. So I multiply by 0.78, 0.78 out of 100, right? 0.78 out of 1, or 78 out of 100. 0.78 atmospheres. Any questions? Let's do an example. To prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. Chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15 grams of neon, and 35 grams of krypton in a piston-cylinder assembly at STP. Calculate the partial pressure of each gas. So the total pressure is equal to the partial pressure of each gas added together. The pressure of helium, pressure of, well, let's stay in order, neon, and the pressure of krypton. And then we also know that for each of those individual gases, the partial pressure, say, of helium is equal to the mole fraction of helium times the total pressure. Do we know what the total pressure is? What does STP mean? Standard temperature and pressure. So the temperature is 0 degrees Celsius, or 273 Kelvin, and the pressure is 1 atmosphere. So we're trying to calculate the partial pressure of each gas, so this equation is probably not going to be very helpful. We're going to need this one. The partial pressure of each individual gas is its mole fraction times the total pressure. We have the total pressure. How do we calculate the mole fraction? The mole fraction of helium is going to equal the moles of helium divided by the total number of moles. So that's moles of helium plus moles of neon plus moles of krypton. How do we find the moles? We got to convert the masses into moles, right? 5.50 grams of helium. So 1 mole of helium weighs 4.003 grams. So this is 1.3739 moles of helium. I have to do this for each gas. 15.0 grams of neon times 1 mole per 20.18 grams. Zero 0.74331 moles of neon, and for krypton, 35.0 grams of krypton. $83.80. So there I have the moles of each gas. So what this is down here, this is the total number of moles. right? So I'm gonna rewrite this a little bit. I'm gonna say the mole fraction of helium is the moles of helium divided by the total number of moles. So the total number of moles is just adding all of these up, right? 1.3739 plus 0.74331 plus 0.41766. My calculator is giving me 2.53487 moles. This is equal to the total number of moles of gas. And if we're going to follow sig figs, this one has 2 decimal places, 3 and 3, so this would have 2 decimal places. So the mole fraction of helium then is the moles of helium divided by the total number of moles. Moles cancel out, fractions don't have units. 0.542 and a whole bunch of zeros. What's the highest that a mole fraction could be? What's the highest number? Could it be bigger than 1? If you take the moles of that gas divided by the total number of moles. If you had a pure gas, then the moles of that individual gas would equal the the total moles, and it would be 1. Mole fractions have to be less than 1, just like regular percentages have to be less than 100. You can't have 110% of the people, right? You can have a 110% error because those aren't things, but these are things. So there's my mole fraction for helium. So I'm going to erase this up here because that didn't end up being useful at all. So the pressure, partial pressure of helium equals the mole fraction of helium, 0.54200, times the total pressure, which was exactly 1 atmosphere, and so this is 0.542 atmospheres. Because the total pressure is 1 atmosphere, the partial pressure is the same as the mole fraction. So let's do neon. Mole fraction of neon is the moles of neon, 0.74331, divided by the total moles. And this is where, like in lab, there's often times where we have to do the same calculation with slightly different numbers. I can just follow the pattern that I did over here. I don't actually have to write all of this down, but I'm doing that for you. 74331 divided by 2.53487. So the mole fraction comes out to be 0.29323, and if I multiply that by 100, I don't want to do that, so I'm not going to. If I multiply by 1 atmosphere, I get the partial pressure of the neon. Yes?
All of these formulas you've given us over the past week are things we're going to have to remember, right?
There's a lot of equations. I will give you a page of formulas. You have to know how to use them, though, right? So you can't just say, oh, well, I'll figure it out on the exam. But I don't want you to get a complicated problem wrong because you couldn't quite remember what the ideal gas constant was, right? And honestly, what real scientists do is they remember the equations that they use all the time, they remember the constants they use all the time, and they know where to look up everything else. So I've got two of these. There are two ways I can find the third one. I can do this same equation, take this, calculate the mole fraction, multiply by 1. Or I can use Dalton's law of partial pressures. The pressure of this plus the pressure of that plus the pressure of the krypton have to add up to the total pressure, which is 1, right? I need more space. So the total pressure of helium plus pressure of neon plus pressure of krypton. That means that the pressure of krypton is equal to the total pressure minus the pressure of helium, minus the pressure of neon. So 1 atmosphere minus 0.542 atmospheres minus 0.293 atmospheres. .165. Let's just double check. Take the 0.41766 divided by 2.53487, and I get 0.1647, which rounds to 0.165. Sometimes the answer you get from subtracting and the answer you get from using the formula, they might be different by a little bit in the uncertain digit. That's nothing to be concerned about. Any questions? We're going to finish this section and then we'll be done. Okay, a sample of hydrogen gas is mixed with water vapor. The mixture has a total pressure of 755 torr and the water vapor has a partial pressure of 24 torr. What amount in moles of hydrogen gas is contained in 1.55 liters of this mixture at 298 Kelvin? So we read the problem and then we pull it apart, we pull the numbers out. So I've got 755 torr, that's a pressure. They're telling me that's a total pressure. So I'm going to call that P, and I'm just going to use T for total. I have hydrogen and water mixed together. So they're telling me that the partial pressure of the water is 24 torr. They're telling me that the volume is 1.55 liters. The temperature is 298 Kelvin. They're wanting the moles of hydrogen. Well, we can use the ideal gas law to calculate moles. The moles of a gas are equal to the pressure times the volume divided by R and the temperature. If I use the total pressure, what kind of number of moles am I going to get? The total number of moles, right? Is that what I want? No, I want moles of hydrogen. This gas is has hydrogen and water in it. I just want to know how many moles of hydrogen are in there. So to find moles of hydrogen, I should use the partial pressure of hydrogen, right? This total pressure equals the pressure of the hydrogen that I want and the pressure of the water. How do I find the pressure of the hydrogen? Subtract, thank you. So, pressure of the hydrogen then is equal to the total pressure minus the pressure of the water vapor. So 755 torr minus 24 torr, which gives me 731 torr. So that's the pressure I need to use. The volume and temperature apply to all the gases in the mixture, so I don't have to mess around with those. Is torr a good unit of pressure for the gas law? No. I need to convert to atmospheres. So the partial pressure of hydrogen is 731 divided by 760. 0.96182 atmospheres. So, moles of hydrogen is equal to the pressure of hydrogen, 0.96182 atmospheres, times the volume, divided by the ideal gas constant, and the temperature. So I'm getting 0.0610 moles of hydrogen. Anybody else?